Okay, so this is example 4.2. So if you remember last time we discussed how we can, let me remind you, last time there was a circuit that was fan out of one inverter. So what we did was that we had one inverter and the output of this inverter was driving another inverter. So this is our VDD, this is our VN, okay, and this is our, let's say, output node Y. So this inverter was driving another single inverter, and we discussed in detail that this transistor has a size of 2, this transistor has a size of 1, and by size I mean width. Okay, so remember that a PMOS has a larger size, okay, larger size than an NMOS. Okay, so because the PMOS, in the PMOS the holes moves very slowly, so it has a large resistance. So if you want to make the current in the series combination the same, you have to increase the current capacity of PMOS, and increasing means you have to use a larger W for the polysilicon. So we discussed this, and we showed that the propagation delay of this network was equal to 6 RC. Okay, so we showed that it was equal to 6 RC. So if you want to review, you have to go back to the slide. Now let's consider another example, which is a 3-input NAND gate. So let me remove this was just for a review. Okay, so we know that the 3-input NOR gate is something like this. It has 3 inputs, let's call them A, B, C, and we have an output Y. Okay, so the input is shorted here, B input is shorted here, C input is shorted here, and we have 3 PMOS. So they are in the pull up network. This is our VDD, this is our ground. Okay, and we have the 3 NMOS connected in the pull down network, okay, in a series. So we want to insert the model, and just to remind you, what is the model, what is the RC model for NMOS and PMOS. For an NMOS, the RC model is something like this, that you have this switch, okay, which represents our transistor, and then you have the drain, and with the drain we have the drain capacitance, which has the size of Kc. Similarly, the drain has the resistance, which is R by K. And then on the source side, we have a capacitor connected here, that is again Kc. And then on the gate side, we have this gate capacitor, which is KC, and this is our gate, this is our drain side, this is our source side. So this is the RC model for an NMOS. We have a similar model for the PMOS. This is just a revision. So for the PMOS, we have a circuit like this. We have the switch. Okay, so we have the switch here, which is represent our transistors, and then we have the drain here. So the drain is below, and we have a capacitor. This is the drain capacitor, it is equal to Kc, and then we have with source we have a resistance. This is our source. The resistance is 2 times R by K, because this is a PMOS, and I told you that the PMOS has a larger size compared to the NMOS to support the same amount of current. So in order for a same amount of current to flow, the size has to double. So this is VDD, and then on the gate side we have the gate, and then we have the capacitor connected to the ground. So note the difference that for an NMOS, all the capacitors are connected to VDD because the N well, you remember how the PMOS are manufactured. They are manufactured inside the N well. So the N well terminal is connected to VDD. That's the reason that all the capacitors are connected to the VDD. So these are our two models. What we have to do, we have to plug in those models into this circuit. So we have to insert this model for every PMOS, and we have to insert this model for every NMOS. So we have to replace all these with NMOS. And okay, one thing to note is what is K. Okay, the K is used several times. It is used here, it is used here, it is used here. So what is K? K is basically the width or size of a transistor. So as I told you before that for an inverter, the size of PMOS is twice the size of NMOS. So in this circuit, how we need to size the transistors? We have 3 NMOS. Okay, so let me compare it again to the case of an inverter. So for an inverter, we had the PMOS and we have the NMOS, and here is our VN, here is our Vout or output. So the size of this was 1, the size of this was 2, PMOS was 2, and size of NMOS was 1. So what we have to do is, you have to understand this thing, that for all the 3 NMOS that are in series, okay, the resistance of all the 3 should be equal to the resistance of a unit NMOS. So this is called unit NMOS. Okay, so in order for these 3 NMOS to have the same resistance or the same current capability, of a unit NMOS, the size should be equal to 3. So the W is equal to 3. When W is equal to 3, what happens to the resistance? The resistance is inversely proportional to W. So the resistance become R by 3. You see in the model here, the resistance is R by 3. So for a series, when you add up R by 3, R by 3, R by 3, it gives you a single R. So that's the logic for that's the logic for how to size the transistors. Now coming back to the PMOS are in parallel. So every PMOS should have the same resistance as a unit PMOS. The unit PMOS is this one. And because they are in parallel, the resistance do not add up. So it is 2, 2, 2. Okay. So we don't need to change anything here because they are in parallel. In case of series, we have to change the sizes. Okay, in this case, the PMOS sizes remain twice the size of unit NMOS. So this is how we determine the size of K. So for any other circuit, first you have to draw the CMOS circuit, the pull up, the pull down, and then you have to come up with the size K, and then after coming up with the size K, we have to insert the RC model for NMOS and the RC model for PMOS. Okay, so let's move to the next slide to see how the RC models are inserted. So you see here that for the case of a PMOS, this is our PMOS. So you see this is our VDD line, and there is a capacitor between the gate terminal and the VDD. Similarly between the drain, and this is our so this is our source for PMOS. This is our gate. Between the source and this is our drain. Between the source we have another capacitor. Okay, so we have this capacitor that goes from the source terminal to the VDD. Now note this capacitor, both the terminals, so this terminal and this terminal, they are both connected to VCC. So basically this capacitor is short, so we can remove this capacitor. Same goes for this capacitor. We can remove this capacitor. Same goes for this capacitor. We can remove this capacitor. Okay, because both the terminals are shorted. So this is the drain capacitor, drain capacitor, drain capacitor. Why 2C? Because from the model we have KC, and K we have found for PMOS the value of K is 2. So that's why it is 2C for PMOS, and for NMOS the value of K was 3. So KC means 3C. So look at the case of NMOS. At every gate, so this is the gate terminal, we have a capacitance of 3C. Similarly at the drain we have capacitance of 3C. We have the capacitance of 3C, but note that this terminal is common. So remember the layout, whenever there were three NMOS in series, so they share the diffusion regions. So that's why, so if you remember that this was the, for example, this was our N region, and we have the poly lines here. So remember that these were shared region. so they have the same capacitances. Okay, so we have another 3C here, we have another 3C here. So this is our equivalent circuit. This was our input A, B, C, and this is our output Y. Now if we remove this these transistors, these capacitors which are shorted, and we sum up all capacitors at input and at output, what will happen? So looking at the input, let me look at input, for example input A. So when I look at input A, I see a 3C resistance here, and I see a 2C resistance here. Okay, so these two resistances are essentially in parallel. Okay, they are in parallel, so I can add up these two capacitances, and I can say when I look into the input A, the total capacitance that I see is 2C plus 3C, which is 5C. Okay, and similarly for the output, if I look into the output, what I see a 2C resistance here, so this goes to the VCC. I see a 2C resistance here, I see a 2C resistance here. They are all in parallel, so 2C plus 2C plus 2C is 6C, and I also see this resistance. Okay, so 6C plus 3C is 9C. So this is my equivalent circuit. If I remove all these, if I remove this, so this is our equivalent circuit. Okay, at every input, so this was our A, B, C, we see a capacitor of 5C, and at the output we see a capacitor of 9C. See that these capacitors stay where they are, and there was another capacitor here, if you remember. So because it is shorted, this one also goes away. Okay, so this is how you convert your input circuit into all the capacitances needed. Now our goal is to calculate the propagation delay, and before we can do that, we can use something for delay calculation that is called Elmore delay. So all the on transistors look like resistors. When the transistors are on, so you just see resistors and capacitors. So these pull up and pull down network are modeled as what is called RC ladder, and the Elmore delay of a RC ladder is this one. So TPD is approximately equal to summation of Ri to source Ci. So let me explain what that means. So for example, this is our node N1. So I start at a node, I see what is the capacitance on the node. So the capacitance on the node is C1, and then starting from the node, I go to the source. So I to source. So I here is 1, node 1. So you see from node 1 to source there is a resistance R1. So we multiply these two, we get R1C1. Okay. Next we come to node 2. Here I is 2. What is the capacitance on the node? It is C2. And then I start from node 2 and I move all the way to the source. So how much is the resistance I see? It is R1 plus R2 into C1. Okay, so we go like this. Then I come to node 3 where I is 3. Again the capacitance is C3 and the resistance are R1 plus R2 plus R3. And if I talk about node N for example, then I is equal to N and I multiply Cn into all the resistances until the source. So R1 plus R2 up until Rn into Cn. So this is called Elmore delay. So often when you convert your circuit into the equivalent RC model, when you apply the RC model and you simplify the circuit, often you will see that you get an RC ladder and the TPD can be easily calculated from RC ladder using this formula. Okay. So let's come to another example. I don't know if this is example 4.3 or something. In this one we have our 3 input NAND gate, and our 3 input NAND gate is connected to H copies of other NAND gates. So this is driving H copies of other NAND gate. So how will our model change? Equivalent circuit change. Remember the circuit from the previous slide. So we had a capacitor of 9C, at the output. Now if we are driving H copies of NAND gate, so what is the equivalent capacitance that appears on the output Y? So remember that every input, so for example this is our input, so looking into the input, what was the capacitance that I see? It was 5C. Okay, so I see the capacitance of 5C at the gates, where 2C is coming from PMOS and 3C is coming from so if let me expand this more. So 3C is coming from here, and sort of let me write this, 2C is coming from PMOS. So in total each input sees capacitance of 5C, and when you have H copies, so 5C is the capacitance of every input and you are driving H copies, so the total capacitance is 5C. That is why the total capacitance at the output is now 9C. This is 9C plus 5HC, where H comes from the fan out. So if we are interested in the propagation delay, okay, so there are two scenarios for the propagation delay. One is so propagation delay TPD is a worst case metric. It is important to understand. What is meant by worst case? Worst case means that, for example, we have 3 PMOS in parallel, and we have 3 NMOS in series. Let us consider that we are moving, the output is moving from 0 to 1. Okay, so what is the worst case for the output to move from 0 to 1? The worst case is when, for example, one of the input, let's say A is 0, B is 1, and C is 1. This is the worst case. What is the best case? The best case is this one. If A is 0, B is 0, C is 0. This is the best case. Why this is the best case? Because this means that all the PMOS are turned on. So imagine if all the PMOS are turned on, the VCC is very strongly driving the output. But if you have one PMOS turned on, so then the VCC is not very strongly driving the output. Okay, so this is the worst case. From the worst case we calculate the propagation delay, and this is our circuit for the worst case. So for example, one of the PMOS is on. When one of the PMOS is on, we have a resistance R that appears here, okay, and that goes to the output Y, and then to the total capacitance 9 plus 5 HC. And we have because A is 0, so we have the lower NMOS off, and the B and C NMOS are on. So you see, this is coming from transistor B, and this is coming from transistor C, for example. So we have R by 3, we have again R by 3, and we have these two capacitances 3C and 3C. So you see, this is node N1, this is node N2, this is node N1, this is node N2. These two transistors are turned on, and the lower transistor is off. So this is the equivalent circuit. So from the equivalent circuit, what is the TPD rise? You see there is a small r. This is for rise. So TPD rise is simply 9 plus 5H into RC. Okay, 9 plus 5H into RC. Okay, so note a correction. So we have a correction here. It is basically, instead of 5, it is basically 15. So basically this is example 4.7 in the book, and I have just noted that there is a mistake in the slides compared to the solved example in the book. So in the solved example, it is 15 instead of 9 here, and how it comes out 15 is interesting, because if we look to the circuit, the output is charged the output capacitor is charged only through the resistance R. That's why here we have R and not something like R plus R by 3 plus R by 3. Why? Because it is only charged through R. So the original Elmore model was something like this. You have a source, then you have a resistance R1, then you have C1, then a resistance R2, then C2, and from here you have the output. So this was the model. But this circuit is different. Here the output is not shared among all the capacitors, but only the output is taken from one node. In that case, we have to count all the capacitors at every node, but the resistances, because they are not on the shared path, they will not be considered. Okay, so this is very important to understand. So we have a propagation delay of rise equal to 9 plus 9C plus 3C plus 3C. When you add all these, it gives us 15C. So the total propagation delay is 15C plus 5H into RC. Note, not R plus R by 3 plus R by 3. Okay, because it is not like this one. Okay, now let me come to the second case. Let me remove this one. These all the things. Okay, so the second circuit is this one, and this is basically for the fall. So when the output is moving from 1 to 0, this is basically for that scenario. So what happens in that case, when the output is moving from 1 to 0, it means that the pull down network is activating. All the NMOS are being activated. Okay, so in that case, what is the equivalent circuit? Okay, so you can say that it is the case when we have A is equal to 1, B is equal to 1, and C is equal to 1. For this combination, all the PMOS are off and the NMOS are on. So the equivalent circuit is something like this one. We have the output Y, on which we have 9 plus 5 HC. Then we have this is the first one. So this is our N2 node, this is our N1 node, so this is our N2. So between N2 and Y, we have a resistance R by 3, because this is R by K, so K is 3. Between N1 and N2 we have R by 3, and between N1 and ground we have R by 3. So this is the equivalent circuit. Now if I ask you what is the propagation delay for fall this is a nice example of Elmore delay. You can see, for example, if we start from the N1 node, so on N1 node we have a delay of 3C into R by 3. On N2 node we have we have a capacitor of 3C into R by 3 plus R by 3. On the output Y we have a delay of 9 plus 5H into C into R1 R by 3 plus R by 3 plus R by 3. Okay, so this is a classic example of Elmore delay. Note the difference between these two circuits. Okay, in one the output is on the shared line, so all the resistors are on the same output line, but in this one the output is not on the shared line, and that's why the calculation was a bit different. Here it was 15C, so this was the correction. Okay, so this is TPD rise plus TPD fall. If you want the overall TPD, the overall TPD is the average of TPD R plus TPD fall. It is the average of this. Okay, so this was example 4.7. So delay has two components. Okay, so basically again this is 15 or 12 RC. In one case it was TPD rise was 15 plus 5H into RC, and TPD fall was 12 plus 5H into RC. So we have two components of delay. This component is called parasitic delay, and parasitic delay is independent of the load. This is the delay of the gate when nothing is connected to the gate. So this is intrinsic delay coming from the gate itself. And then we have the effort delay. So this is the effort delay, and this is basically equal to the load capacitance, how many things you have connected to the load. So delay has these two main components. Next is we want to calculate the contamination delay. This is basically example 4.8. Okay, so remember, a contamination delay is the best case delay. And we are interested in finding out the contamination delay of 3 input NAND gate. So it is the same example. So what we can do, if all the 3 inputs fall together, what will happen? If all the 3 inputs fall together means that we have A is equal to 0, B is equal to 0, and C is equal to 0. This was our A, this was our B, this was our C. This is the best case. In the best case, what happens is that VDD is connected. This is one PMOS through R, another PMOS through R, another PMOS through R. So these three resistances are in parallel, okay, and basically if you calculate the equivalent resistance, it will be R by 3, and you see that the supply is strongly driving the output. So the capacitors will receive a much larger current in this case. Okay, so what will happen? What will be the delay in this case? We can write the TPD fall, which is 9 plus 5 H C into the resistance R by 3, which is the equivalent resistance of the parallel combination, and it will be, if we apply this one, it will become 3 5 by 3 H C H into R C. Okay, so this is our entire propagation delay for the fall. I can write it here. So if maybe I have to remove, so it is 3 plus 5 divided by 3 H into RC. Let me remove it from here. So this is the propagation delay for the fall. Sorry, this is the propagation delay for rise, not fall. So it is basically TPD of rise. So note the rise. Why rise? Because all the pull-up network are activating. So you are pulling up to the VDD. So that's why it is that's why it is the rise delay. Okay. For the fall, TPD fall, please do it yourself. It is already given in example 4.8. So try to solve it yourself and then check example 4.8 if you are unable to do it yourself. Okay, so this brings us to the final let's say final slides, and we are interested in looking at the layout, and we want to see which layout is best in terms of propagation delay. Okay, so consider this layout in the slide. Okay, you see that the output, so this is our output line, this is our output. Two transistors, two PMOSes are on the shared line. Similarly, if we look onto the VDD, that's how it is connected. So you see that these two transistors share the same capacitance. Okay, so it is shared diffusion capacitance. And when you lay out your circuit like this, that this PMOS and this PMOS has a shared capacitance, then at the output, because this is the output line, at the output, instead of 9C, which was for our 3-input NAND gate, instead of 9C we have 7C. Okay, so this is sort of a layout kind of view to explain which layout will have better delay. Let's try to understand this with these two layouts. So these are the stick diagram, and what are these? Basically, it is a two-input NAND gate, because here we have a PMOS, here we have a PMOS, here we have an NMOS and NMOS. These two NMOS are in series. The above two NMOS PMOS are in parallel. Again, on this side also we have a PMOS, an NMOS, and NMOS. They are in series. What is the difference? The difference is on the left side we have two connections for VDD and a single connection for output. On the right side we have a single connection for VDD, and we have two connections for two contact points, so this one and this one, two connections for our output. Okay, so which one is better? Which one is better? This one on the left or this one on the right? Okay, so on this side, let's consider the right one. We have a 2C capacitance from here and a 2C capacitance from here. So these are in parallel, so the capacitance will add up. Why 2? Because these are PMOS. PMOS are double the size of NMOS. But on this side, the transistor A and B have a shared region, and that's why the capacitance is counted only once. So this means that the layout on the left is better in terms of delay than the layout on the right. Okay, so this brings me to the conclusion of this lecture. This lecture is very important in terms of how we can plug in the RC model, and after plugging in the RC model, before plugging in we need to size the transistors. So we need to determine this the parameter K, which is the width, and then we need to plug in the RC model, and then we need to calculate the equivalent circuits for best case and worst case. In case of TPD we use the worst case. In case of TCD, we use the best case. So I want you to carefully watch these lectures and practice some examples. I will also give you an assignment on these topics. So let's stop here for this one.